and we will introduce Dr. Romit Maulik. He's an assistant professor of IST, also with ICDS. And he also have a joint appointment with Oregon National Lab. And I guess I'll leave the stage to you.
Great, thank you. Short and sweet, that's how I like it. So anyway, so thank you everyone for being here. Thank you, Danning, for the invitation. So my name is Romit Maulik. I'm a new faculty here in Penn State. I'm in the IST department. But I have a background in mechanical and aerospace engineering. So you may be curious how someone with a background in mechanical and aerospace engineering ends up in the information science department. So I hope to satisfy your curiosity today through the talk. So I was talking to Danning about how to set up this talk, and I realized that since I'm just a 5-minute walk, I don't know, I can't do cardinal directions. 5-minute walk towards Westgate. My office is E327 Westgate. That if there's any questions you have, you can just feel free to knock on my door and get clarification. So the talk over here will be a cross section. So it's going to be for the first half part, I'll give you highlight slides of the various things that we're doing in the lab, and then I'll dive deep into a couple of studies which I think you might be interested in. Okay. So in essence, each highlight slide I give you has its own talk. Happy to go through all of these later, right? All right, so what sort of work do I do, right? So I like to start with this Venn diagram on the left, which tells the audience, what sort of work I'm doing. Frequently, people think I'm a computer scientist. They think I'm a high-performance computing person. Of course, I have a PhD in mechanical and aerospace engineering, so they also think I'm an engineer. But what I like to tell people is that I'm at the intersection of all of those. So in the middle of the Venn diagram over there, which is a field that has many names. You may have read papers with titles called physics-informed machine learning, physics-informed deep learning, scientific machine learning. I like to use the word scientific machine learning, which means that it's the use of data-driven methods for science, not for classifying cats versus dogs, right? Or for giving you recipes for cakes. That's also stuff that machine learning can do, right? So it's at the intersection of HPC, machine learning, and computational science. In practice, what we want to do is we want to address problems across all of these domains with the methods that we build over here. But you'll see the box around this Venn diagram that says domain science problems, right? So what we really want to do is we want to identify a grand challenge problem in a variety of domains, and you'll see some examples today, and then try to build algorithms to solve the grand challenge problem. This is slightly different from how people typically build methods in applied mathematics, which is they'll take 1 or 2 dimensional problems, prototype their methods on these 1 or 2 dimensional problems, and then take a step forward towards getting bigger and bigger. And but this is something that's up for debate, and you probably have your own opinions about this. The way data-driven methods are trying to solve these methods is definitely a more bottom-down approach. They go right to the big problems and see if things work. So that's more like a philosophy rather than a claim. In terms of facilities, as I said, I'm here at Penn State, so I've got the same facilities like a lot of you do. So I have actually one PhD student who's sitting with me in the audience. Thanks for raising your hand. But in addition, I also have a very convenient sort of joint appointment at a national lab, which gives me access to a very large number of compute resources and also their own programs for hiring. So by the way, that required a lot of lawyers for talking to each other between Penn State and Harvard. So I've set that up. So if you're interested, you can talk to me about this. Okay. All right. So the first half of the talk is some highlights, right? It's meant to be an informal type of talk. So feel free, if you think that a particular highlight slide doesn't have all the necessary details, feel free to stop me and interrupt me, and then we can continue. Okay. All right. So what do we I guess try to build here in the ISCL? We start with, for example, something that probably several people in the audience are familiar with, which is the idea of building surrogate models, right? So in recent times, well, not in recent times, but historically, fluid dynamicists have kind of invested quite a bit of time and effort in building reduced order models of dynamical systems due to the promise of them accelerating how much time it takes to execute a computational campaign. So this could be something like if you want to build a linearized approximation of your dynamics for use in a control type loop, or a design optimization type strategy where you just need many query sort of evaluations of your forward model. So for example, some of the works that we have done mainly rely on in constructing reduced order models by compressing our original system. So if your original system is generated by a very high dimensional partial differential equation, right? The discretized partial differential equation, it's got all the ugly things that are involved with, for example, quadratic nonlinearities, turbulence, and so on. If you can find, as I show over here, a representation, a manifold on which qualitatively the same solution can be obtained, but at a much compressed representation, then you can basically accelerate the process of finding your answer within reason, right? These are not, these are not going to replace your PD-based methods. So, but they will accelerate something. So for example, a couple of applications that I continue to work on are, for example, building reduced order models or emulators of satellite observation platforms, right? So if you think about satellites collecting snapshots of data in real time, I believe the fidelity that you can get on the websites, the NOAA and NASA websites now is about 10 to 15 minutes. So it's almost real time. But let's say now that you want to use these things to make a forecast type of system. So some of the things that we do are, for example, using, ideas that as fluid dynamicists, we should be very, very comfortable with the use of things like proper orthogonal decomposition, right? So principal components, linear compression methods to identify a set of latent coordinates. And then within this set of latent coordinates, using machine learning algorithms, I will explain this flowchart in greater detail in a while, to build forecast models, right? So identify coordinates, that can involve machine learning. In this case, it uses a data-driven method. Some people like to call it ML nowadays, but POD is, 40 years old at this moment, right? So using the singular value decomposition effectively to identify a set of coordinates. And then in those set of coordinates, use approximations of your dynamics. These can be using machine learning algorithms. These can be using linear regression, right? To build very, very fast dynamical systems emulators, okay? Other things that we do with surrogate models is something related to what I call closure, not in the sense of turbulence. How many people are familiar with turbulent closure modeling? So a couple of hands. So let me define the term closure a bit over here. So closure, if you're talking about turbulence, is trying to model scales that cannot be computed, right? In the sense of statistical physics, closure is often looked at bridging particle representations of your physics versus continuum representations of your physics, okay? So if you think about the continuum representation of your of a flow as given by Navier-Stokes, but a particle representation coming from some sort of kinetic equation, then some of the methods that we build in our group involve looking at particles and approximating densities, right? So if you have a density, you can sample from the density and get particles. You can also go the other way around using modern methods in approximating density. So over here on the left, for example, the plots that you see that go from left to right are actually a school of fish that are evolving. Each dot over there, it was a experiment where they recorded fish schooling in a plane. I believe there was some vertical movement as well, which they could not capture. But the idea is, can you build a time-varying density which represents the schooling of the fish, right? So over here, you can ignore the second row. That's just another algorithm. The colored dots are samples from the density we were able to learn of particles moving in time, right? So we were able to follow the thing. So what did we get as a result of this? You can see something like this up here on the top right. Even though we had observations of particles of a certain behavior, we were able to build a smooth representation of the density from which these particles could be sampled, right? So this is slightly different from building surrogate models that I showed you in the previous slide, where we looked at continuum representations and we built continuum surrogates. Here we looked at particles that were evolving and we were able to extract an underlying density from the particles. Okay. Why is this useful? Well, there are many types of physical systems where you do have this sort of scale type separation where you would like to do your modeling at the continuum scale, but perhaps your observations are not in the continuum scale, right? They're particle scale. So if you think about PIV, I don't know, there's some chances of it. I've never worked with PIV personally, but maybe you can brainstorm some ideas. Okay. And of course, the methods that we look at, there are various methods. I'm not a method evangelist over here saying my method is the best, all you guys should go home. I think a problem and a tool go hand in hand, right? So there are different methods to do this. Some have their pros, some have their cons. You could use linear methods to do this. Of course, they won't be as good, right? But for certain problems, perhaps, why not? Okay. Other things that we work on include this concept of model and data fusion. So what we like to do, if you go back, if you think about the slide I showed you right at the top over here, which is start with a domain science problem and then try to address it head on, grab the bull by the horns, right? That's kind of something that I'm trying to pitch with these machine learning methods. So I don't know how, I'm sure all of you read papers. So I'm sure like me, all of you are rather tired of looking at papers with flow around the cylinder for machine learning, right? So for example, I'm guilty of the same thing. I've also published a flow around the cylinder paper, but I'm happy to report that this was about 4 years ago. I do not do flow around the cylinder papers anymore. I think I've matured as a researcher. So for example, on the top left, no, that doesn't mean you cannot do flow around. Feel free to do it if it actually adds value, okay? So this is a study I did with a grad student intern while I was at Argonne, where what we were trying to do was we were trying to look at experimental data on the surface of a cylinder, as you can see. Let me use my pointer, right? On the top left, and try to reconstruct the flow field, right? Honestly, this is overkill, in my opinion. You don't need a very complex machine learning algorithm to do this. You could do this with, honestly, like a linear type of method. It's flow on the cylinder with your periodic vortex shedding, it's laminar, it's not fun, right? But we did it, and people have done these types of things, and this thing got published as well, so I'm not claiming anything, to the contrary of what I did. But for example, to take this idea, right, the idea of looking at experimental data and then reconstructing a flow field that was obtained from a simulation, right, is, in my opinion, a pretty nice opportunity for actually involving experimentalists in your predictive modeling project at a very early stage, right? Rather than building numerical models and then doing an a posteriori sort of validation with experimental data, you can include them in the process of building your predictive models at a much earlier stage, right? To give you an example of how we actually took that and used it on a real problem with experimental, sort of collaborators. On the bottom left is a topographical map of an onshore wind turbine farm in the Texas Panhandle, okay? So the red dots that you see over here are the wind turbine locations. And it's not very clear, but the X over here is a LiDAR station. So this is basically scanning the atmosphere. I'm not an experimentalist. I could have some crude explanations, which feel free to correct me, but scans the wake behind these turbines to calculate the wake deficit. The triangle over here, the yellow triangle that you can see on the bottom right, is a MET station. So this is a station by the state government of Texas that's taking readings of the temperature of the atmosphere, the amount of mixing in the atmosphere, the time of the day, and so on and so forth. Okay, so my experimentalist collaborator at the University of Texas in Dallas said, hey, Romit, it'd be really great if you can build me a virtual LiDAR or a data-driven LiDAR. What that means is, he said, I don't want to go into the field and collect these measurements again and again. I do have data from my last campaign, which took him 3 months to collect these images of the wake deficits behind these turbines. And he also had data about the state of the atmosphere from the Met Tower. So the goal was, in a manner similar to what I have up here, if I have information about the Met Tower and I know the altitude of the particular wind turbine, or let's just say the label of the turbine, make it even more simpler, can I reconstruct what the LiDAR image would have been, right? And he's an experimentalist, so he said, I have a large margin of error, Romit. So give me anything because I just don't want to go out there, right? So over here, so the approach that we used was, we go back to our idea of reducing the dimension of our original system and identifying a coordinate like a non-linear transformation into a latent space where using information from the yellow triangle, the Met Tower, right, and giving it the information about which label that we were looking at in the wind farm, we were able to reconstruct a 4-dimensional representation of the flow field in the latent space, and then use the map back from the latent space to the original space to reconstruct his experimental observations. Okay. And of course, once you have everything in the 4-dimensional space, it's rapid. We ran it on hardware that was as easy as a cell phone, right? So the idea is, will this replace his LiDAR instrument? Absolutely not, right? But this is a way to accelerate, let's say, a campaign, or at least understand, to a crude level, very cheaply, maybe what is happening on his wind farm, right? So that's an example of, say, the top-down approach to the algorithm that we built over here was honestly very, very trivial, right? Most of the work that went into curating the data, he did all the work. He gave me the data, he cleaned it, right? So I guess I'm trying to say, if you can think on a larger scale, your machine learning methods can actually give you greater benefits. Okay. Oh, by the way, one of the co-authors of this paper is a faculty in the Department of Aerospace Engineering, Dr. Ashwin Ranganathan. Okay, so we work together on this. So I've talked about the use of machine learning methods. One of the greatest sort of benefits of using machine learning methods is that they accelerate things, right? So, well, not always, you will see, not always, but it's a good approximation, 0th order approximation, to say that the machine learning methods that you've built should be faster and more inexpensive than running an experiment or actually running a PD solver. Not always, but it's not a bad approximation. So one of the things that we like to do with, once these methods are constructed, is then use them in outer loop applications, right? So what outer loop applications do people generally look at? These are things like optimization, control, query of designs, many things. So, you folks are all from the aerospace department over here. You probably know a lot more about this than I do. For example, some of the things that we looked at also with Ashwin is how to do shape optimization of transonic airfoils, right? Without using adjoints, right? So without using the adjoint of a CFD code, we use the adjoint of a surrogate, right? So if you build a machine learning surrogate model of your map from design to quantity of interest, in this case, the quantity of interest was lift constraint drag, where we wanted to minimize drag, constraint to a certain lift, and then perturb the shape of the airfoil. So this was defined by some polynomials. So you perturb the coefficients of the polynomials and you get a different quantity of interest. If this map is a differentiable map, right, you just construct a loss function with respect to the quantity of interest, differentiate back through the map. Because it was a neural network, this differentiation is rapid. You don't need to solve an adjoint equation with all its headaches. And again, am I saying don't use adjoints of CFD solvers anymore? Not at all. In fact, my group is using adjoints of CFD solvers for other things. It's what you could use these methods for is really zoning in on a sort of a space of solutions that are good before switching to something that's more reliable, right? So not replacing CFD, but augmenting it dramatically, right? So to give you an example, if you think about these columns that I have over here on the left, this is an approach that uses a classical approach, like an adjoint-based method to give you a result. You're looking at each adjoint solving approximately 2 times the cost of a regular PDE solve. So for each design that you need, right, you're looking at, I don't know, 3x the type of computational cost. This may vary from problem to problem, so these numbers are not set in stone. In contrast, what we have with the use of a surrogate model is what I call amortization, right? So you have to run designs of CFD solvers between the shape to to the quantity of interest several times a priori, use that to build your surrogate model, right? But online, you don't have to evaluate your PD anymore. So next time you're reviewing a machine learning paper, right, make sure you ask them, what is your amortization rate? Right, this is something that people don't ask. So they'll say, we ran 10,000 simulations and we got a surrogate that is so much faster than all these simulations. Fine. But how long will it take for you to recover the cost of those 10,000 simulations, right? So in this particular work, by the way, the references are all in the back. I'd be happy to share the slide. In this particular work, Ashwin and I, we set ourselves a very strict budget in the sense of how many simulations we were allowed to run. 50, no more than 50, right? And so the novelty in this particular paper was that when setting ourselves a budget of 50, we looked at two scenarios. The first scenario was we used all of the 50 to train a surrogate model, right? And then did this surrogate-based optimization. And this gave us a result, for example, in the bottom left. So this is a trace of the coefficient of pressure versus the chord length. And so what I have as true over here, we didn't know the true solution over here. What I have as true over here was Ashwin running a very, very large experimental design, 2,000 simulations to find the best possible shape, right? So I don't know if there's a unique solution to this, but he said, consider this to be the truth, get close to it, right? I had 50 simulations to train my model, right? He had 2,000 to search for the truth. And based on the different trials I ran this multiple times. You see, it was not very satisfactory. I wasn't able to capture the exact location of the shot. Okay, we went back to the drawing board and we said, okay, how about we use 40? Remember, 50 is our upper limit. We cannot use any more for training data. How about I use 40 to train my model, but then during the optimization process, I give my model the luxury of 10 simulations to try using the real PD solver. RANs in this case, okay? What does it look like? So basically, I mean, those are details, but in the algorithm, the neural net or the surrogate that I was building with the 40 simulations gave me like a guess. I used the 40 simulations also to identify a bias because using the training data, I can see how off I am using the 40 simulations. And then using the bias, modeled as a Gaussian process, I was able to do acquisition of new points. So wherever my bias was high, I went there and put a new point there, but this point was computed using a PD solver. When I still used 50 simulations, right? But I used 40 for training, 10 for a real-time acquisition of high fidelity data. And so you can see I've computed in terms of amortization, I still have the same compute cost, but I get a much better solution, right? So generally, machine learning methods for for fluids applications, you will have a very predictable structure to the paper. They'll be like, here are the set of equations. Here are the simulations we ran. Here is how we split it into training and testing. Here is how we fit it. And once we fit it, everything was amazing, right? But I'm saying that there are shades of gray in between, right? You can keep using simulations to get a better outcome, okay? Okay, any questions about that? So I want to talk, yes.
So you're handling high dimensional data, at least that you can characterize with an image. So when faced with problems like this, sometimes I've wondered, is it best to resort to the neural networks that are already structured to accommodate images? Or are you treating the things that are displayed as images as matrix quantities and then trying to predict a matrix and you're just showing it as an image?
Well, this is way simpler than what you just said, okay? This is just coefficients of polynomials.
Well, yeah, maybe this isn't the best slide for that, but I think some of your other slides, like with the LiDAR data, like you had.
So the LiDAR data was structured because my experimental collaborator was kind enough to give me everything on a polar coordinate grid, r by theta, so I could send it in as a matrix. But you'll see later on in my slides, I do deal with unstructured data as well. It's possible, right? So we use graph neural networks to deal with unstructured data.
Yeah.
That actually makes, that's actually a big peeve I have, my pet peeves with a lot of machine learning literature out there as well, which tend to use structured representations and declare victory, right? So saying that there's a lot more work that needs to be done.
But even if it's structured, if it's high dimensional, so if you're trying to predict a a high dimensional quantity, even if it's structured, that still doesn't seem to me a really easy thing.
Cursor dimensionality is some people will come and tell you that using neural networks, not machine learning, neural network methods help you beat the cursor dimensionality because there are a few theorems that prove that the leading order term for approximation does not have D in it anymore, but that introduces assumptions of smoothness, which they don't talk about. So high dimensional but smooth to me means low dimensional. So cursor dimensionality cannot be bypassed, in my opinion. Yeah. Okay. So, but we would like to at least start being competitive with linear methods, like like classic linear system solvers, that are used in PDs to solve for very, very high degrees of freedom using machine learning methods, right? We're still not even there yet. So, outperforming PDs is way in the future, but or PD solvers is way in the future, but we need to build methods that can get close first. Okay. So now this slide particularly talks to some of the grad students in the audience. So this is there is a term in machine learning which is called graduate student descent. How many people have heard about that? Graduate student descent. Gradient descent, right? You use gradients to go towards an optimal solution. Graduate student descent is the graduate student comes every week to your office and says, I tried this. And you say you tried that direction. And so with neural networks, frequently when you have to train things, you have to use, use is a bad term for a human, but you have to ask grad students to basically try different combinations of architectures and hyperparameters. And it's very frustrating for both the PI and the grad student. And so some of the things that I've been looking at with a few collaborators at Argonne and Oak Ridge National Labs is automating the process of discovering, for example, neural architectures, but this is a more general framework for function approximation, right? So what do we do over here? So we say, okay, then there's this software package out there called Deep Hyper. It's on GitHub. It's really easy to install and use. And if you have a distributed resource as low as 8 GPUs, you can parallelize the search for neural network hyperparameters, but also neural network architectures. And if you learn the API sufficiently well, it also lets you search for symbolic functions, symbolic regressions. So the idea over here is this. If your search space for any sort of function approximation, if your search space can be represented as a directed acyclic graph, right? So what is a directed acyclic graph? You have nodes and edges. At each node, there are multiple options to choose, right? Now, what these options are, you decide. And the edges are connectivity information that a search algorithm will choose, okay? So for example, let's say you're trying to fit a neural network. So how many people have tried to fit a neural network? Even partially, I guess almost all of us now at this point. So you could have a decision to put a certain type of layer. This could be a identity layer, which means do nothing. This could be a dense layer with a certain number of neurons, which means, have a dense layer. It could have a certain activation. You can choose, for example, to have a skip connection that does skip or does not skip, right? So if you set up a graph with options like this and have an outer agent, again, an outer loop application, an outer loop agent, go in and select options, right? In parallel, you can evaluate lots of architectures, lots of structures, show it to some validation data, train these, of course you have to train them. Based on how good they are, you can use evolutionary pressure to get better and better architectures, right? No rigor at all, I'm sorry, right? This is completely, evolutionary algorithms don't give you any guarantees, but empirically, we have observed cases where in this process of using, associating a choice, a set of choices with a good reward, which is good accuracy, and using those as parents, mutating them and involving them while throwing away bad architectures, you get progressively better function approximation, okay? So if eventually the outer loop algorithm that works with this is just looking at a long list, if you're talking Python, a list of integers, where the entry of the list is a node, a choice, right? So let's say you have 4 choices of that list, you have option 0, 1, 2, 3. In the second entry of the list, let's say you have 8 choices, you have 0, 1, 2, 3. So you can see this explodes, the space explodes, it's very rich, right? But you can interpret this list as a gene, which means at each iteration, once you evolve it and you say that this gene is my best candidate, it's given me the best accuracy, I flip one of the chromosomes inside, right? So something was a 7, and the number of options is 10, so 0 to 9. So I say np.random.randint 0 to 9. I change that, that becomes a new candidate. I evaluate that. Was it a good option? Did it improve on the previous? That's the evolutionary pressure, right? So this lets you actually automate the process of discovering architectures. There's another nice thing that comes out of this, which is that if you have a sufficiently large resource, a computational resource, you can get a catalog of architectures, right? So generally what we see that when this process starts converging, the way we measure convergence is on some held out data set, how all my architectures are performing. You will see if you look at the performance of the top 10 architectures, they start growing over time, right? And then they start flattening. That's the time to stop the search because they're flattened, right? But if you take the top 10 architectures over here, let's say I found 5 good architectures. These architectures are completely alien to each other. They don't look alike at all, generally, okay? But you've basically built an ensemble of function approximators. And now that you have an ensemble, convergence notwithstanding, but you can assume that these are samples from some underlying density and then do uncertainty quantification of your function approximation, okay? Convergence notwithstanding. We have not addressed issues of convergence, but you can do a mean prediction, a variance prediction. You can decompose your variance into epistemic, which is model, aleatoric, which is data. And this gives you, again, going back to this problem over here, this gives you the ability to make a forecast with a surrogate model, right? Which is not just a point prediction, right? So it's going to give you a mean absolute error, but it's also going to give you, for example, as you can see on the left, it's going to give you estimates of uncertainty, both data and model, right? So this is something that's nice. Any questions about this? So this is a very easy to use technique. If you have a neural network that's coded up in TensorFlow, which I think ChatGPT can do for you in 2 seconds now, right? You can, this thing works on top of any TensorFlow commands and functions. So there are tutorials as well on GitHub. I have done some development in this code a couple of years ago. So there may be some changes, but if I'm not sure on ICDS, it shouldn't be very difficult to deploy this. And so one thing I'm interested in doing, and this is a little bit of my research work that of course depends if someone funds it, but is now extending this to do some sort of scientific discovery, right? So now I'm discovering architectures. You can say the discovery of a neural architecture in some sense searching for a hypothesis. But how about we make it more formal? How about we put options over here in the search space, for example, in the output? How many people have fit a pin in the past, like a physics-informed neural network? Okay, well, that's good. You could have regularization terms over here that could be inspired by physics. Okay, you could have representations of your input that are a library, right? So now you can search for convenient representations of your problem, convenient regularizations, which then reveal something about the function you're trying to approximate, which nobody has done, by the way, right? I would very much like to do this. So it's kind of like a scalable, parallel hypothesis search, not purely for fitting something with a neural net, but also for extracting some maybe learning, right? So yes.
So here you're searching for essentially an expression, right? So how do you put a regularization on the simplicity of the expression?
So maybe like an L1 type of penalty, like some of the Cindy stuff.
Well, but here since you are describing it as a DAG, right? So it's like
So describing it as a?
As DAG, right? The graph, right? As you're using a
DAG, yes.
Yeah, right.
Yeah.
So how do you regularize this sparsity or simplicity on the graph?
We won't put a simplicity on the graph, only on the output terms.
Oh,
You see, so this has not been done yet. So maybe there is an option to even penalize for the sparsity on the graph. It's possible, yes. But what we will do is we will make some choices on our graph. We will get a neural network, and we'll get a loss function as well, because there'll be some choices for the loss. And then on the loss, we'll put a sparsity for the regularization only. It's much more simpler than what you're saying. What you're saying is you want to ensure sparsity also on the options, right? I can give you a half answer for that question. So the half answer is that this particular approach, the outer loop intelligence does not care for the reward. You have to design the reward. This reward could be very simple, like the accuracy of the neural network, but it could also be some feature of the neural network. For example, we do have a reward which penalizes the number of parameters. So if for example, you compute a reward, the accuracy is very high, but the number of parameters is 2 orders of magnitude higher than, another member of the ensemble, you could choose to have a reward which is accuracy scalarized plus or minus some function of the number of parameters. Okay, that's completely fine. But I don't know how to provide a sparsity constraint like you were asking, which is on the graph. But the number of parameters which will engender sparsity, that we can do. And so some experiments I've run, for example, which are not published, and I don't have the time to write them up either, is choices for precision at the nodes, right? You could choose the number of neurons, right? You could also choose what representation you want the weights to have, 16, 32, 64, right? These are options that you can specify. If there are 3 options and then 4 types of layers, so 4 into 3, 12 options at a particular node point, at a particular node. And so now you have mixed precision, architectures that you can also work with, right? And it does select mixed precision type of networks, which are far easier to store in memory than tower precision. So again, not published, but a lot of possibilities, right? Okay. All right. So that was sort of a segue into some of the outer loop things that kind of we have been working on. Other outer loop things that we've been working on is the use of reinforcement learning for the purpose of I call it for scientific computing. So reinforcement learning is, in my opinion, a very like a cousin of control, which with some relaxations in kind of how you frame the problem. But the idea is that you have an intelligence that sits atop your computational workflow and then maximizes for a particular objective, right? By approximating gradients rather than exactly calculating gradients, right? So adjoints require exact gradients. This does not. So, for example, one study that we did that I quite liked, but has since been relegated to the footnotes of history because I don't have students to work on it. I have 2 students now, but they're busy with other things. Is how to control a numerical solver with reinforcement learning, right? And by control, not invasive control, non-invasive control. So if you think about how many people run OpenFOAM or some CFD solver over here, it's probably a lot of knobs that you have to tune before you get a converged result, right? And that's for getting a converged result. There's a lot of knobs you have to tune for getting it fast enough, right? So in OpenFOAM, if you're running an incompressible solver, for example, for flow or a backward-facing step, you have the relaxation factors for velocity and pressure that you have to tune, right, to get a converged result. So you have a matrix over here on the bottom right. Based on the combination of the relaxation factor for pressure and velocity, your code can converge as quickly as 600 iterations, zero-time iterations for incompressible Navier-Stokes, steady-state Navier-Stokes, or it could never converge, right? It could blow up, okay? So, so in this particular study, what we did was we used a reinforcement learning agent to not do anything to the physics of the problem, but just to play with OpenFOAM. Like just like you see those videos of it playing video games, I said, keep fiddling with the velocity and pressure relaxation factors over time, with the goal being that you accelerate time to convergence. Okay, and so something that we discovered over here was that it realized initially these graphs were very ugly, but it realized over time that I don't touch the velocity relaxation factor. I keep it as high as my state space allows, which I'll set the highest point to be 0.9. And then it said the pressure relaxation factor, I'm going to keep playing with it. And when it did that in real time, so this is iterations, it learned policies, it learned methods to tune the open form simulation so that in general, we were always converging faster for a class of problems. So during the training, each simulation, I used different Reynolds number, different step height. But this was all done on the open form side, right? So the RL problem did not really touch open form. And so over here, because I don't know how much time I have, I just want to quickly tell you something. This code is actually available on GitHub. It's called parallel, sorry. So it's receinforcement learning that's wrapped around OpenFOAM, a CFD solver. There are certain examples over here for recreating the same problem I showed you, but also for a shape optimization for an airfoil, optimizing PD constants for matching some quantity of interest. So if people want to work on that and collaborate on that, I'd be really excited to do that, right? So and this sounds easy, but it took about a year to actually plug this in together. This is also parallelized, by the way. So one agent runs multiple open form simulations on different nodes, calculates rewards, decides to then tweak its parameters, runs multiple simulations. So I'd be excited to try it for some of your problems. Okay, let's see. So what else could you do with something like this? So like I said, this is basically a method that controls your simulation in a sort of like a non-invasive manner, right? So maybe this slide could have been before the previous one for more impact. But so I'm sure all of you have played around with the Lorentz equations for dynamical systems, for hyperbolic chaos and dynamical systems. So the parameters of the Lorentz equations, which generally we play around with, are, for example, rho is 28, right? Which causes this beautiful butterfly attractor, right? But if you choose a value for rho, which is say 20, you end up getting fixed points, no chaos. The thing is stable, right? So one paper that we published on this was, okay, can we use reinforcement learning to keep perturbing these parameters, even though they are in expectation? In expectation is stable configuration. Okay, so in expectation, my rho is 20, but because I bounce rho by certain percentage points over time, I continue to remain chaotic. Okay, so each time step, my reinforcement learning agent would look at the state, look at the derivative of the state, and based on these information, it would then apply a perturbation of delta something to the parameters. And then the numerical solver would take one step, and then it would apply another perturbation. And we would play this game in such a way that, well, in the long term, we would have this sort of attractor shape emerge, right? So if it did not emerge, bad, do something better. If it did emerge, you're doing the right thing, right? And so this is one way in which you can think about reinforcement learning as control, right? As control. Very costly, very poorly constructed control, but as your state space for actions grows, it starts getting competitive. So generally speaking, whenever I have conversations with people who are RL people for fluids versus gradient people for fluids, which I am, right? I tell them, if you have the gradient, why are you not using the gradient? Because RL is just approximating the gradient, right? So I tell my students this as well. So don't use RL if you can find the gradient, okay? So of course, backpropagating through a chaotic system has its own headaches. We are in the process of solving that. But when you have the gradient, use the gradient. Okay. Okay, how much time do I have?
5 minutes.
5 minutes? Oh boy, so I should come back here a couple more times, I think.
Sure.
Let me stop with this. Okay, so I promised you at the start that I like to take the bull by the horns, and then I haven't done any wrangling of bulls yet. So I'll give you one example where we did build a surrogate for the realistic weather problem, and actually close the loop as I promised, right? Using real world data and kind of improving forecast. So this is a project that I have in collaboration with Argonne and Microsoft, where we are writing up the results at the moment. There's a preliminary paper online. It's a project to build a surrogate model for the entire weather. Okay. The atmosphere, not the ocean. Okay, that's a very important distinction. For the atmosphere, we have a historical data set called the ERA5 data set. This is collected by the European Center for Intermediate Weather Forecasting. It's I want to say, a 4 terabyte, maybe even more data set, which is 41 variables of the Earth's atmosphere. So velocities, pressures at different heights, on a grid of 1440 by 720. So you can see the input space now is very high, right? 1440 by 720 by 41. And our goal is to ingest this cube of data and predict the next time step at a 6-hour cadence. Okay. And so for this particular work, we used a deep neural network because we could not find a lower representation. We could not compress this anymore. It was very, very large, very, very turbulent, very chaotic. It's the weather. And for this, I will not spend time on this because I don't have much time, but we used a vision transformer, which is state of the art in core machine learning for learning function approximations on structured image data sets, right? And the nice thing about this was we picked this up from a GitHub repository that Microsoft had released, okay, which goes to the whole reproducibility aspect of things. We picked this up from Microsoft and we just retrained it for a bit, okay, using some new data. And so again, I won't go into this. These are all in the paper. This is just the architecture of the neural network that does the prediction. What you need to know is we have this cube of data that goes in. We get a cube of data at t+6 hours, okay? So just to give you an example of how complex the data set is, so I'm plotting over here on the right the specific humidity in the contours, and the arrows, I don't know if you can see it, are the wind vectors and over the Eastern Pacific. Question for the audience, which one do you think is the truth between the left and the right? The one on the right, I hear this is a very intelligent audience. I like it. People can be confused about it. The one on the right is stuff collected from satellites. The one on the left is the prediction from our model. So for, of course, if you keep running our model into the future, it diverges, right? This is a problem with weather models in general, which you can't trust them. But you see, just to fine tune this data, we required 12 hours on 40 A100. So this, it may sound like a cool dynamical systems research problem, but it was actually an engineering research problem, a software and hardware engineering research problem. How do you map this large neural network onto 40 GPUs, do model parallelism, data parallelism? So I learned a lot about the problems that you'll end up with if you take machine learning and apply it to a prototypical CFD or dynamical systems problem. It's not the algorithm. It's the hardware, it's the software. Even the simplest architecture will require a lot of engineering before it works. So I think it's good to start there so that you know what you're, so for example, how many of you know about ResNets, residual neural networks? Doesn't matter. A ResNet is an architecture that's very popular in a lot of 1D and 2D problems. I tried it for this. There is no hardware that exists that can fit a ResNet in memory for this type of problem. So basically, why are we using ResNets, right? I mean, if you have to solve problems like this, we are going to suffer if you don't, think about these issues with scaling, okay? But the nice thing about now having a solver that runs on one GPU instead of an entire cluster, a data center for PD solutions, right? The National Weather Service has these massive massive data centers, high-performance computing facilities to make simulations for the weather and so on. But now this model that I showed you over here, once it's trained, it can be, you can run it on one GPU on a workstation, right? Because that's the whole promise of machine learning, is that you can set up a Bayesian inference problem to now assimilate data in real time very quickly. Okay, so what I have in this equation over here, Canning, if you'll permit me 2 more minutes, is an approach where I set up an objective function of my trained model. So my model is trained, it's fixed. My objective function is saying, if I do have some real observations, from the real weather, right, in real time, if I have some real observations, can I tune my model output or model parameter or model input? Can I tune it so that I match, at least at those locations, I match my real weather more accurately? And this is actually done even with your standard PD-based solvers. That's the forecast you get on your phones. Okay. The issue is you have to differentiate the left-hand side, like del J by del X, right? And set it equal to 0, because you have to minimize this objective function. To do this, when h of x is a PD, requires adjoints. You have to take an adjoint through an incredibly complicated system of equations, right? The weather. Now, h of x is a torch function. To compute d by dx of h of x is just loss dot backward because of automatic differentiation. Right, that's the benefit of these methods, right? The outer loop application. So once we do that, we looked at some real world observations of weather balloons launched and then collected data. This is, and I won't go into this anymore. I'd be happy to come back and give you more results, but we were able to see that in comparison to a regular model, which is the green one, without using the real world data, the machine learning model the error was growing over time, but by using actual, ignore the blue line, by using actual observations from the sensor locations, we are able to keep the error bounded, but at a fraction of a cost that it takes to do it for the original system, because the original system would then require adjoints. Actually, the original system builds a linear surrogate of the model. That's something called the TLM model. So what we have over here is actually a slightly more accurate approach than the original method. So I guess I want to impress on you the fact that once you have a surrogate of a dynamical system, there are all these approaches within which you can accelerate a computational campaign. However, you must note that in my talk today, I did not say if you have a surrogate, throw away the original PD. I've never said that. Okay, it hurts me in my job applications also. So it's good to know that these are a very competitive tool that you can have in addition to your classical computational methods to engender predictability for complex systems. Okay, I can talk about this. There was a question about unstructured methods. I do have research on unstructured methods where graph neural networks can work on unstructured flow fields. Be happy to come back in the future and give you more information about this. But thank you so much for your time, and I'll take any questions. By the way, you don't have to ask questions. I'm right here.
Question in the chat, if you can.
Oh, it's just Vic saying he had to leave.
Oh, okay.
So my office is E327, right? So happy to chat with all of you. If you have ideas for projects, collaborations, my doors are open.
I would have followed.
Yes.
Well, most likely have some prediction of PDF of the particles.
Yes.
So that one seems very similar to the particle filters when we do state estimation.
Exactly.
So have you
Yes.
thought about using that to integrate with the state estimator?
I'm writing a proposal on it,
Okay, great.
which will, I'm sure, get rejected. So I'll talk to you about
I had
it.
a similar question. Particle filter approach, yeah.
Yes. Yeah. So, but the nice thing over here is that lets you bypass Gaussian assumptions.
Unless you.
Bypass Gaussian assumptions, because so the algorithms that we use over here let you learn arbitrary densities from particles. Smooth ones, but arbitrary ones.
Okay. Well, thank you. Romit. Thank you very much. and
Absolutely.
Be happy to have you come back and talk more about your search. We do have some sandwiches and drinks. We're not allowed to eat in the room, but feel free to take those to go back to your offices or to hang out in the hallway after the meeting. If you
Grab a sandwich before you go. so you don't
Thanks for
hurry.
coming up.
Absolutely. And
Nice
thank
to
you for
meet
the
you.
invitation. Yeah. Likewise. And thanks a lot.
Yeah, yeah. I mean, that's a serious thing, like, I don't think that it's included at all.
Oh, okay, okay. Cool.
So, that's, let me say.
Very nice to meet you. Yeah. Model, right?
Multimodal information.
Combined with some